Hello, good morning, good night, good evening, whenever you see this video. I'm going to keep on solving some exam type exercises in the topics of numerical series, and we are for the next half an hour again on the series of positive terms. So, and let me go back to the ideas that we developed yesterday. Yesterday we talked about prototypes for numerical series. The prototypes are series like this, 1 over n to the power alpha, where the power alpha is positive. Okay, so by using basically the comparison principle and other principle, we were able to solve some simple exercise. Of course, these are not the only prototypes we have. We introduce another family of prototypes or refined prototypes. But why are they useful? Because varying alpha, the behavior of the series varies. For alpha equal to 1, there is a transition from convergence to divergence. So they provide a useful family of prototypes. But of course, there are many other possibilities for series. And so it is quite important to understand how the generic term decays as n goes to plus infinity. I just recall you, not a theoretical lecture, but I just want to point out some ideas. And the first idea I want to point out is that in order to be convergent, so if the series is convergent, then the generic term of the series is infinitesimal, goes to 0. This is the first point. Vice versa, it is not true. If the generic term goes to 0, you could have a divergent series. Okay, think of the harmonic series. Okay, so let me says that if an goes to 0, then the series is convergent. Is false. This is false. Okay, I want to insist on that. This is very elementary, but a huge fraction of students always makes this mistake. Prove that the series is convergent. Okay, the generic term an goes to 0, then the series is convergent. Wrong, totally wrong. Okay, I will punish very hard with this sort of mistake. So understand it and remember it. I don't want to go into theoretical detail. You can find in theoretical lectures, you can find in books. But for the exercise, just be acquainted with this very simple rule. On the other hand, the same logical statement here can be reversed in a correct way. And we say that if the generic term does not go to 0, then the series is not convergent. Okay. Does not converge. This is very simple to verify, and we will see some example in future lectures. Okay, is it clear? So this is the first thing. Then you could be asked to determine the behavior, the character of a series whose generic term goes to 0. And then you can act by comparison principle, for instance. So compare the speed of decay of an with the speed of decay of 1 over n to the alpha, and then by comparison, decide whether the sum of AN converges or not. I will go slower here. So, you see that the generic series is sum. I will put only infinity here. It's not important, the starting point. AN. Let me start with AN, again, non-negative. So, non-negative terms, so this series either converges or positively diverges. Okay? What decides whether it converges or positively diverges? The speed of the decay of AN to infinity. So, what is important here is the speed of decay. This is the point I really want you to underline, to convey to you very strongly. It is not sufficient that AN goes to 0, it must have speed enough. If you are confronted with 1 over n to the alpha power, alpha decides the speed. The larger alpha, the faster the decay to 0 of the generic term. Okay? And so the larger alpha, the higher the possibility that it converges. And we know that there is a threshold at 1. If alpha is larger than 1, then this series converges. Okay, because alpha changes this speed of decay to infinity. Now consider another series with non-negative terms. And it is a good idea, often it is a good idea to compare the speed of decay of the AN you are considering with the speed of decay of the prototypes. Very simple. And in order to do that, you should remember what you studied in analysis 1 about the comparison between different sequences, different infinitesimal sequences. And you know that 1 over log n to some power beta, this goes to 0 as n goes to plus infinity. But this is much slower in the sense that the generic term is larger, to 1 over n to the alpha power. Of course, beta is larger than 0, alpha is larger than 0. And the series with this generic term are divergent. Here we have a threshold. But then this is much larger than 1 over a to the n. This is exponential with a larger than 0, 2. Then I will write that all the quantity of the parameters here, beta, alpha, and a are larger than 0. And this is much larger than 1 over n factorial. And this is much larger than 1 over n to the n. Okay, remember this scale of infinitesimal sequences. Perhaps you are more familiar with the inverse scale of the infinite sequences. So the logarithm is much smaller than any power, which is much smaller than any exponential, which is much smaller than any factorial, which is much smaller than n to the n. Probably you know that, but now we apply to infinitesimal sequences because we have to decide whether a series converges or not. Now, since here, for these sequences, the corresponding series can converge or diverge depending on alpha. The threshold is here. Here there is alpha equal to 1, which is the threshold. For alpha smaller than 1, and for all the series here, we have divergence. And for all the series here, we have convergence. So once you know this table, it is extremely easy to do an exercise like following. For instance, sum for n going from 0 to infinity of 2 to the power n plus 3 to the power n divided by 5 to the power n. The first question is to study the behavior or the character. Notice that here you see exponentials. When you hear exponentials, exponentials are likely to converge. Then we will study it a bit better. But study the character. And so you take the generic term an, which here is 2 to the n plus 3 to the n power divided by 5 to the n. So this is equal to 2. You can do it in many ways. A nice way to do that is to say 1 over 5 over 2 to the n plus 1 over 3 over 5 to the n. Okay. Now, of course, what I forgot to tell you is that here a must be larger than 1. Sorry, this is 5 over 3. I told you in the last lecture that I'm likely to do mistake. Today, I already made some mistake, okay? 5 over 2, 5 over 3. So they are both larger than 1. So these two terms are exponentially decaying. So taken separately, these two terms give rise to convergent series, because this is 1 over a to the n for a larger than 1. Also, this here 1 over a to the n with a larger than 1. Okay. Then here you have to deal with sum of convergent series. A sum of convergent series is convergent. Okay. And once you realize that you are dealing with an exponential decaying series, then you make resource to this simple schema, to this simple comparison scheme. And exponential is here after 1 over n, after the harmonic series. So everything converges. But there are also some families of series that can be also explicitly computed. So studying the character is very fast, but if you want to compute the series, you have to work a bit more. In this case, this exponential, precisely exponential terms give rise to the so-called geometric series, and geometric series can be explicitly computed. I know you already studied that, but so another question, first question, study the character, the second question can be compute the series, find the number, okay? So this is the first question, the second question is compute the series. And let me do simply this computation. Consider the series sum b to the power n. Okay, you already know this result, but let me recall it to you. For b sorry smaller than 1 this time. And of course, by definition, this is equal to the limit for capital N going to plus infinity of the sum for n going from 0 to capital N of the quantity b to the n. And what is this guy here? So again, the limit for capital N going to plus infinity. This is equal to 1 minus b to capital N plus 1 divided 1 minus b. Now you have to take the limit, n appears only here, so we have a number which is smaller than 1 in, of course, positive number. Today we're talking about positive series. And this has n, it's exponential, that is an exponent, so when the exponent goes to plus infinity, this is a small number, smaller than 1, so it goes to 0. So the result is that this guy goes to 0, and so finally you have 1 divided by 1 minus b. So this is the formula you have to apply. Okay? And so I cancel it out. I hope that in your notes you noted this guy here. And so let us do the first passage here as before. This is equal to sum for n going to infinity of 1, or let me do simply 2 over 5 to the power n plus 3 over 5 to the power n. Reasoning like before, we know that these two terms give rise to convergent series, so we can split it. Otherwise, we could not. Okay? So before writing that this is equal to the sum of 2 over 5 to the n power plus the sum of 3 over 5 to the n power, here you are using commutativity and associativity of sum. This is true for finite sum. For series in general, it is not true. But for convergent series, for positive series that are convergent, this you can do. But first, in order to justify the passage, you must ensure yourself that these two guys give rise to convergent series. Okay? So 2 over 5 plus 3 over 5, and then this is our b is this guy here. Let me call it, for instance, b1, and this is b2. So we apply our formula. This is equal to 1 divided 1 minus b1, which is 2 over 5, plus 1 divided 1 minus 3 over 5. And so at the end you have here 5 here at the numerator, and here you have divided by 3 plus 5 divided by 2, and this is equal to the common denominator is 6, and so 10 plus 15, so we have 25. Is it correct? 2 times 5 is equal to 10. 3 times 5 is equal to 15. So we end up with this result. But it will be quite uncommon that we give you a series and ask you to compute the result. If we do that, it is because we know that we have easy method to do that. Okay, there is something a bit more complicated, which is with Fourier series. We will see it when talking about Fourier series. But so 2 messages. First message: when you have exponential decay of the genetic term, the series is convergent. You don't have to add anything more. First. Second, if you have a geometric series, then you can compute the result. So you can give the number. So this is all for this exercise, and let me look for other exercises to be solved. Yes, I want the factorial to come into play. Because sometimes the comparison can be less immediate, and so, for instance, let me here consider this sum n going from 0 to infinity of 2 to the nth power divided n factorial. Okay, so premise from the previous scheme I gave you. We know that, so a remark is the generic term to the nth power divided n factorial goes to 0 as n goes to plus infinity. But remember that it is not sufficient, the fact that the generic term is infinitesimal, to ensure us that the series is convergent. It must go to 0 with sufficient speed, with a sufficient rate, faster than the harmonic series. This is the main message. It is not perfectly correct. Yesterday we saw a series that has terms faster than 1 over n, faster than the harmonic series to go to 0, but it diverged. It was 1 over n log n. But the harmonic series, when we are dealing with power, is a threshold. The threshold can be more refined. Remember what we said yesterday. Okay. However, here it will be sufficient to use the power. So we have to decide whether 2 over n factorial goes to 0 fast enough. And so let me try to compute in a very, very elementary way this term. This means that we have n times the factor 2. 2 by 2 by 2. This is repeated n times. N factorial, it means that it is 1 times 2 times 3 times 4 and so on and so on. And you end up with 2 over n here, and here we have 2 over n minus 1. Okay. Now, it can be useful here to make an estimate. So 2 over 1 is equal to 2. This is equal to 1. 2 over 3 is less than 1. Then all other factors here are less than 1. So what we can do is to estimate all this guy here by 2, because this is 2 times 1 times something which is less than 1, and so on and so on. So we can say that the generic term of our series is smaller than, here from this yellow bracket we extract a factor 2. Here we have another 2 and another 2. So totally you have 8 divided by n minus 1. Now, first, we go fast. Here we have a quantity that gives rise to a series which is convergent because it goes like 1 or 8, it's the same, 1 over n squared. And in our prototypes, when you have 1 over n squared, it is convergent. Since it is smaller than the generic term of a convergent series, then also this guy is convergent. Okay, this is very fast. This is the speed I want from you at the exam. You should not have anything to add here. But since here we are in a sort of a lecture, then let me explain. So I copy the conclusion from elementary estimate. We have that the generic term of the series is smaller than a divided by n minus 1. Okay? For every n larger than 1. But now, let us compare this guy with the prototypes. And so, for instance, here we can say that 8 divided by n times n minus 1 is smaller than what? Is smaller than, for instance, we can add something here to the 8. Let me double it, 16 divided by n squared. Okay. Wanted to exaggerate, put in 16. Do you see it? Here the problem was that this n minus 1 makes this denominator smaller than x squared. So since it is smaller, I cannot just put here 8 divided by n squared. But the correction due to this factor becomes negligible as n becomes larger. So it is sufficient that I put here a number which is larger than 8 and I'm safe. But let me prove it. So just go to the common denominator. Here you have 8 n squared less or equal to 16 n squared minus 16 n. So I'm saying that 8 n squared, sorry, let me say 16 n is less or equal than 8 n squared, and this is obvious. As n becomes larger, this is eventually true. Okay, so this is true eventually. Eventually means from a certain n on, and once this is true, eventually then you are safe. You can apply comparison. Okay. You can also use a more straightforward argument. Instead of comparing, just make an equivalence. 8 divided this guy is equivalent to 8 over n squared, and this is convergent. Okay. Once you grasp the fact, once you grasp that this coefficient is going to 0 faster than any other faster than a certain power, which gives you a convergence, and then you apply the criterion you prefer. Also, the integral criterion here will give you the answer immediately. Okay. But the main point is looking at this and try to understand whether its decay is faster or not. This is the only non-trivial, somewhat non-algorithmic path. Sometimes you have to have some ideas on that. Good. We are already at half an hour, so I would like to stop here.